So the concept of attenuation led engineers to start dividing regions geographically into what we call cells. Now, we're not speaking of a biological cell, clearly, so don't get confused there. We're speaking of a cell in terms of a cellular network or a cellular system. And the way that we represent a cell is geometrically, as a hexagon. So we divide our region into a bunch of hexagons. And the reason that we divide them into hexagons is perhaps beyond our scope here. We can point out one important idea. And one of the reasons is that at the intersection of each of these cells, we have what we call cell towers or base stations. And rather than having a base station in the middle of each cell serving to the ends of each cells, we have one base station serving a portion of 3 different cells. So a third of it would serve this portion, a third of it would serve this portion, a third of it would serve this portion, and so on. So that's one of the reasons, and the other ones are perhaps beyond our scope here. So now, within each of these cells, we have our phones, and each of our phones or our mobile subscriptions lie within one of these cells. And we call cell phones, or any device that can transmit and receive according to a cellular standard, a mobile station, or an MS. And the MSs are going to connect to base stations depending upon where they are. And another term you may have heard for base station could be node B, or evolvable node B, meaning E node B. That's a 4G term, and we're not going to use that term here, even though you could call it node B or E node B, depending upon what you're speaking of. For our purposes here, they're really synonymous. So we'll just stick with the term base station. So now, with FDMA, we have to determine which frequency band to allocate to which cell. And with the cellular network, there's certain rules that this imposes upon that from having a detrimental impact on conversations. So what we say with the cellular network is that each cell is going to get a band of frequencies. So naturally, within each cell, they're only going to use one band of frequencies, but each mobile station has to be on a different channel. So if this is the channel allocation for this cell, each mobile station within this cell is going to be on a different one of these channels. Each of the adjacent cells to this one, so this cell right here is adjacent because it's touching, this cell is adjacent, and this one's also adjacent. Each of them has to use a block of frequencies that's different than the one that this cell is using. So this cell up here would have to use a different set of frequencies than this cell over here. But as long as the cells are not adjacent, we can reuse the existing frequencies. So up here, for instance, in this cell, we can use the same frequency bands that this cell down here is using because they're far enough away that the attenuation will cut down the signal level so far when we travel from here up to here that you won't even be able to hear the conversations anymore, even if these people are using the same frequency bands as the ones in this cell. So we have to determine how to allocate the bands of frequencies in order to use the minimum number of channels, because that will clearly be the most spectrally efficient, as we would say, or it's making best use of our available capacity. So that's a pretty difficult problem mathematically if we have a really large cell region to determine what each cell would get, what frequency band each cell will get, so that we conform to these ideas of only reusing if the cell blocks are non-adjacent, as we said, and using the minimum number, because that's the most spectrally efficient, is to use the minimum number of frequency bands. So we can look at this simple example, though, because it's small enough and we can just eyeball what each would be in order to use the minimum number. The way that we can go about doing that is by assigning each one a different color, and a color here will be a band of frequencies. So we can start by coloring this first cell blue over here. And now, as we said, these are each adjacent to this blue cell, so we have to color them a different color than this blue. So we'll choose red, green, and orange maybe. Now, let's try to color this cell over here. Now, this cell is adjacent to green and red, but it is not adjacent to either blue or orange. So we could color this either blue or orange. And so rather than adding a fifth color or a fifth set of frequencies, we can reuse, as we choose this orange over here, to make it more spectrally efficient, which means that we're making better use of our available frequency capacity. We could have also taken this orange over here and made this one green, because these are not adjacent, but we just chose 3 different colors off the bat over here, because then this one would not have been able to be green, it would have had to have been orange. So it's still using 4, and so we just want to make sure we're using the minimum number of colors possible. Now, we can continue to allocate colors to each of these cell blocks, and we might get something like this. And there's not only one answer, there's different allocations clearly that would work, but the idea is that we just want to make sure we're using the minimum number of colors possible, because that's going to give us the maximum use of our available capacity. And so you can verify in this diagram that no 2 adjacent cells have the same color. And that's the idea. That's what we want to get across here. And so if we look at a frequency chart down here, just to draw this out, we may say that the blue is on channels 1, 2, and 3 if there were only 3 channels within each frequency band. That's clearly not anywhere near enough, but just for illustration purposes, we would say that these 3 would be 1, 2, and 3. So now anyone in the red band would use 4, 5, and 6 to allocate to their cell blocks, which is separate from 1, 2, and 3. So separate color, separate bands. And 7, 8, and 9 for green, and 10, 11, and 12 for orange. So now, as we have more and more channels within each frequency block, we would need to add more spectrum. So we would have to increase the size of this accordingly. But right here, we're just showing 3 for each, for a total of 12 channels divided accordingly. So rather than needing... So now, we're using 12 channels to allocate to this entire spectrum in here. So we need 12 channels to do this allocation if we want each cell to have 3 channels. So now if we count up the number of cells, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if we wanted to give each cell a different band of frequencies, we would need 13 times 3 per cell, which is 39 channels. And we're doing this in only 12. So we have that factor of improvement. Instead of 39, we've now reduced it now to only needing 12 to do this same allocation. So clearly, using cells gives us a lot of capacity advantage over not using cells. Now, one other term we should point out is that of the frequency reuse factor, which is exactly what we were just discussing here. The frequency reuse factor is the number of colors that you need in this diagram. It's really the number of bands that you need to use. So in here, we have a frequency reuse factor of 4 because we're using 4 different colors or 4 different bands of frequencies. The cellular concept marked the transition from 0G to 1G technology. And the first such 1G or first generation technology was called AMPS, or the Advanced Mobile Phone System, which was introduced in the United States in 1978 and in other countries a little later. Now, the first field trial of AMPS was in Chicago, and it consisted of 10 cells and 90 people. And AMPS operated in the 800 megahertz band. And this really demonstrated the feasibility of the cell concept, and the cell concept is employed to the present day. Under AMPS, the number of mobile phone users skyrocketed. In the United States, by the mid-1990s, there were already around 25 million mobile subscribers.